So today is lecture number 9 of Introduction to Physical Metallurgy class, and today's content are 5 Platonic solids, and second one is what is the condition to call whether it is a plane or whether it is a solid. The third is the structure of this is actually football uh, and carbon 60, and what is lattice parameters. These are the 3 contents of today's lecture. So Plato is a research scholar, you can say. He's a great researcher in uh, geometry of solids. Right? He did a lot of work on this. What is the geometry of different solids? He was more interested in that to find out the geometry of solids. So you can see that 430 BC. So he's the most famous philosopher at that time, at 430 BC. So polygons means poly means many, gons means side, you can say, or face. Fine. Then regular polygons means what? They have same edge length or side are same. The best example of regular polygon is equilateral triangle, for example. In equilateral triangle we have all the 3 sides, or you can say all the 3 edges are same, right? The square is again a regular polygon. Similarly, Pentagon, again all edge length are same. They are regular. That means the edge length are same. Now solids. So how you can define what is a solid actually? So once somebody is saying it is a solid, that means it has 3-dimensional geometric shape, right? Obviously, any solids you take, they have that is in 3 dimension, and they have a particular geometrical shape, right? But what is the interesting part of that? This one. And at least 3 sides of the polygons meet at a point, and the total internal angle between them be less than 360 degree. This part is more important. So you can understand solids will involve these polygons, right? If you carefully look at into solids, they will involve polygons which I told many sides will be there, and at least 3 sides of the polygon meet at a point, right? So when the 3 polygons will meet, at least 3 polygons will meet at a point, if angle will be there, so total angle, internal angle should be less than 360 degree, then only it will be a solid. Now, difference between a plane and a solid. What is the difference between a plane? Because the regular polygon can meet, they can form a plane or they can form a solid, right? So total angle if less than 360 degree at vertex or corner, it becomes a solid, and if more than 360 degree, it becomes a plane, right? You have to remember that. Suppose you take square, you take 2 square, you take 4 number of squares, they'll make a plane. You join at the vertices, right? And you can measure the angle also. But if you take 3 square and put them at the vertices, like in form of a cube. So cube is a solid, right? You can measure the angle, inside angle of a cube, where the 3 squares are meeting, right? In a cube, obviously, you can see 3 squares are meeting at a point at the vertices, right? And you can measure the angle, and that angle will be obviously less than 360 degree. Right? So that means you understand my point. If the angle is greater than 360 degree or 360 degree at least, it cannot be a solid. It will be a plane, right? Then Platonic solids. So as I told, Plato is a philosopher. You can call him as a very good researcher, who studied a lot about geometry of solids. So according to him, we have 5 solids, Platonic solids, 3-dimensional and regular solid objects. So what are those 5 Platonic solids? Those are tetrahedron, hexahedron, octahedron, dodecahedron, icosahedron. So these are the 5 Platonic solids. Right? We'll see that what exactly those are. And you have to remember this hexahedron is sometimes in simple way we can call it as a cube. But we can have other form of solids also. But they are truncated version of these 5 solids. Fine. Actually, what happens? According to Plato, the entire universe is made up of these 5 different type of solids. We cannot have more than these 5 different kind of solids, right? So entire universe is made up of these 5 different kind of solids. Question may be like this: why we cannot have more than 5 kind of solids? Because of this one. This is the limitations. Total angle if less than 360 degree at vertices or corner, it become a solid, right? We'll see that soon. Okay, so these are the Platonic solids. Number of faces here written over here, and these are the images you can see. So first one is the tetrahedron. You can see this is a tetrahedron. The same solid tetrahedron is here. I have put both images. Both are tetrahedron. You can see. So 4 triangular faces are present. Tetra means 4. Hedron means faces. You can say simply. You can see this is 1 face. This is 2. Behind that we have 3, and at the bottom we have 4. So when the 4 triangle will meet, 1, 2, 3, and bottom on 4, it will become a tetrahedron. Tetrahedron Platonic solids. So simple tetrahedron, right? You can see here also. This is 1, this is 2, this is 3, and at the bottom, just opposite to this vertex, we have another triangle, right? That is 4. Then hexahedron. Hexa means 6. Hedron means faces. So we have 6 square faces, right? You can see 1, 2, 3, 4, and top on 5, bottom on 6. Right? So it's the solid one here. Next one is octahedron. Octa means 8. Hedron means faces again. So this octahedron is made up of 8 triangular faces. Just have a look. If you look at this one, then we have this face 1, this face 2, this face 3, this face 4. Just behind this one, another 4 triangles will be there. So 8 triangle faces will constitute the octahedron. Right? It is also shown over here. Also, you can see this one is 1, this part is 2, this part is 3, and behind that is 4. So below also we have same. This one is 1, 2, behind 4, and 5. 1, 2, 3, 4, 5, 6, 7, 8. Total is 8. You can see. Then dodecahedron. Dodecahedron is basically 12 pentagonal faces will be present. This kind of structure you can see. This is a pentagon, right? This is, you can see, pentagon means 5. This is 1H, 2, 3, 4, 5, right? This is formed by triangles, this is formed by square, this is formed by triangle, but this is formed by a pentagon. So we have 12 pentagonal faces. Then icosahedron, here 20 triangular faces is present. You can see triangles are here. Like this we have 20 triangular faces. We will consider icosahedron. So these are the 5 Platonic solids, and these are the images. And these are the number of faces we have. And you understand triangles, squares, pentagons, they constitute these solids, right? And triangle, you have to remember always it should be equilateral triangle, right? Now this is also very interesting slide. You can see regular solids. Suppose I am taking 3 equilateral triangle. If you suppose just have an imagination right now. We have 3 equilateral triangle. Suppose you meet them at a corner point. at the vertices point, right? Just imagine the three equilateral triangle are meeting at a point like this. Otherwise, suppose consider this point, for example, this point. This is one triangle, this is another triangle, and at the bottom another triangle will be there, right? Bottom triangle, this triangle, and this triangle, they're meeting at a point, right? Just imagine. So what will happen? Total internal angle at each corner. So total internal angle will be how much? Total internal angle will be calculation 16 to 3, right? Because internal angle in a triangle is 60 degree. So we have three triangles, so 16 to 3, that is 180, right? So if this is the situation, then the solid form will be tetrahedron. So you can take a tetrahedron, like you can measure the internal angles at these corners and at these corners and at these corners, you'll find the same, that is 180 degree. And you can just remember, I've told you what this one. Total angle if less than 360 degree at vertices or corner, it becomes a solid, right? So obviously tetrahedron is a solid now. Tetrahedron solid, fine. Similarly, 4 equilateral triangles, fine. So just imagine you have 4 equilateral triangle and they are meeting at a point, forming a corner or vertices, right? So the total internal angle formed will be how much? 16 to 4, because in a triangle the internal angle is 60 degree, equilateral triangle, right? So 16 to 4, it is 240. So again the condition is fulfilled because it is less than, to form a solid, this is the condition, right? The total internal angle is less than 360 degree, right? So it will form octahedron. You can check octahedron here. This one, this one, 2, 3, 4. They are meeting at a point. Suppose this one. You can measure the angle. It will come out as 240. Okay. Similarly, suppose you just imagine we have 5 equilateral triangles. They are meeting at a point, forming a corner vertices, right? So total internal angle formed by the 5 equilateral triangle will be how much? 16 to 5, that is 300. So it is also below 360 degree. So total internal angle is below 360 degree, means it will form a solid again. So it will form icosahedron, this one, right? Now next imagine we have 6 equilateral triangles. Suppose 6 equilateral triangles are meeting at a point and forming a vertices and corner, right? So total internal angle formed by this 5 equilateral triangle will be, sorry, this 6 equilateral triangle will be 16 to 6, 360 degree. So can you tell me now, if this is 360 degree, whether it will form a solid or not? If the total internal angle gives,
Plane.
yes, it cannot form a solid now, because you can see the maximum value should be less than 360 degree, but now this is 360 degree. So if you take 6 equilateral triangle and meet them at a point to form a vertices or a corner, you will get the angle of 360 degree. So this condition is not fulfilled. So what I have written, for a solid, angle must be less than 360 degree. So no solid will form. Instead of formation of a hexagonal plane, right? It will form an hexagon kind of thing. You can draw it by yourself if you want. Take 6 equilateral triangle and put them and form meet them at a vertices. You'll find it will be a tile kind of thing, or a plane will be there. Next, suppose so you can understand, right? Equilateral triangles will lead to formation of tetrahedron, formation of octahedron, formation of icosahedron. So these are the, this one, and this one. But now square, suppose, and if you remember, I have told you minimum 3 regular polygons should be there to form a solid, right? At least 3, right? That's why I haven't taken any 2 or 1, right? So now 3 squares, you take 3 number of squares and put them so that it will form a vertex or it will form a corner. So total internal angle formed by these 3 square at a corner will be how much? In a square, the angle in a square is how much? 90 degree. So 90 into 3, so it will become 270, right? So this condition is also fulfilled to form a solid, because total internal angle is less than 360 degree. So it will form an hexahedron, which is simply called cube. Just have a look. You measure this angle otherwise. this angle will be less equal to this much, 270 degree. You understand that this is 1, this is 2, and this is 3. They're meeting at a corner point, right? So to form a cube, you need 3 square at least. Then 4 square. If you take 4 squares, they'll meet at a point to form a vertices or corner. So total internal angle formed by this 4 square at a corner is 19 to 4. It is 360 degree. So now can you tell me this will form a solid or not? If you are taking 4 squares. So no solid possible because the limitation is it should be below 360 degree. Right? No solid will form. Now pentagon. Pentagon 5 faces, right? Or 5 edges now. So 3 pentagons. So total internal angle formed by the 3 pentagons at a corner will be, in a pentagon the angle is 108. So it will be 108 into 3, that is 324. So solid will form, and that is dodecahedron. This one, dodecahedron. You can see pentagons are there. And how much pentagons I have written here? 3 pentagons. You can see this is a pentagon, this is a pentagon, and this is a pentagon. They are meeting at this point, forming a corner vertices. You can measure the angle. It will be coming as 324. So it is less than 360 degrees. So dodecahedron will form, right? I think you understood the points. Now the structure of carbon-60. The buckyballs, you have gone through that in chemistry or physics, I think. In chemistry, obviously. And football structure. The structure of football, which we used to play. So football and carbon-60 have same kind of structure. This is the structure of football. This is the structure of your carbon-60. Both structure are same. But how they are made up of? They are made up of combination of hexagon and pentagon. If you take only hexagon to make a football, you cannot make a football. But you cannot make carbon-660. If you take only pentagon also, you cannot make them. You can make a football. You cannot make a football out of that. So combination of hexagon and pentagon will be there to give rise to a football structure, or structure of this carbon-60. You can see here also. You can see this is 1, 2, 3, 4, and 5. So this is a pentagon, right? But how to find out hexagon now? Just look at this one, this part. This is 1, 2, 3, 4, 5, and 6, right? So this is a pentagon, this is a hexagon. So combination of pentagon and hexagon will give rise to a football structure or structure of carbon-60. Only pentagon cannot do that, only hexagon combination cannot do that. You have to remember this structure, fine. Okay, next moving into the symmetry of crystal structure. So this is a very interesting part, but we'll not cover this one today, symmetry of crystal structure. But rather than we'll cover something else, that is this lattice parameter. What is lattice parameter? See, I think I will tell you something about lattice parameter right now, but what is a lattice exactly, I will cover that in the next lecture better. What is a lattice, what is a crystal structure, what is a basis, what is a unit cell, all, and what are the different crystal system, what are different Brabis lattices, all I will cover in the coming lecture. Just for explanation, just have a look here. This is a structure, and this is also a structure. This is a structure and this is also a structure. Can you people tell me what is the difference in this structure and in this structure? Just have a look and tell me.
Sir, their sides are different.
Sides are different. Okay.
Sir,
They have number of sides or face, better to say face, are same or not? Here the face are same, here the number of faces are same. That is common.
Yes, sir.
But what is the difference?
Sir, in the first figure, all the sides are equal in length, and in the second figure, A is equal to B, but they are not equal to C.
Very good, very good. So you can see here, this is a cubic structure. If you remember, I was talking about a lot of things about this structure of iron. Iron basically takes a structure of cubic structure, basically. It may be body center cubic or it may be face centered cubic. Depending upon the temperature, it changes its crystal structure, right? So we can have a cubic structure like this. This is actually simple cubic structure. You have to remember, this is neither body centered nor face centered, or not edge center. This is only simple cubic structure. Simple cubic structure means in this structure you can see this is a cube, right? And atoms are present only at the corners of the cube. This is a simple cubic structure. But here, what is the lattice parameter? The lattice parameter is nothing but the edge length of this cube. So this, just have a look at this colorful part, this one. This is one edge length, this is another edge length, this is another edge length, right? You can consider this one also. This is one edge length, this is another edge length, this is another edge length, right? All the edge lengths are same. You can consider, suppose we are considering this as an origin. So this is suppose A, and this one is B, and this one is C, right? And it is a cube. That means all the edge lengths are same. So that is why A is equal to B is equal to C. So we can call this edge length as A, this edge length as B, this edge length as C, right? I think it is okay up to this. So this A, B, and C are one of the lattice parameter, right? So different lattices may have different lattice parameters. If you consider different metals, this lattice parameter is not always same. It is variable. It varies from one element to another element, basically. But if they have same crystal structure, if two elements have same crystal structure, that means this one is same. A is equal to B is equal to C, right? You have to remember that. And second lattice parameter is the angle between this. Here, this is one angle, this is another angle, this is another angle, right? So you have to remember, if you are considering this as an A as length, so just opposite angle will be this is the this angle is between the two axes, interaxial angle, you can say. This angle, its name is alpha, and this is B as length. So opposite to this will be beta. This interaxial angle will be beta, right? And if this is the Z, this is C, actually C, then opposite interaxial angle will be gamma, right? So this is alpha, this one is beta, this one is gamma, which is shown over here. Okay, let me blow it up. It is visible now. Alpha, beta, and gamma, right? This is A, this is B, this is C, right? So this alpha is equal to beta is equal to gamma here in a cubic system. That is equal to 90 degree. Sorry, any questions? Okay, so now just compare this structure with this one now. Somebody have answered it well. You can see in a tetragon, this is called tetragonal. This is called tetragonal structure. In a tetragonal structure, this is A as length, this is B as length, but this one is C as length, right? So here as length A is equal to B, but as length C is larger compared to A and B. So that's why A is equal to B, but not equal to C. Or C is greater than A and B, right? So it is written over here, A is equal to B, but not equal to C. So in this structure, the lattice parameter A is equal to B, but not equal to C. Fine. And if you determine the interaxial angle, the interaxial angle are 90 degree like this one, cubic system. This is, if you remember, this one is alpha, this one is beta, this one is gamma, right? So alpha is equal to beta is equal to gamma is equal to 90 degree. So earlier what happens, people thought that this lattice parameter A, B, C and the interaxial angle alpha, beta and gamma, these are the main reasons why we have different crystal system. But this is not true actually. The truth is the symmetry of the crystal structure. The symmetry of the crystal structure classify different structure into different crystal system. Right? We have different crystal system because of this difference in symmetry. So symmetry will decide which type of crystal system we have. This is just for knowledge. This lattice parameter. Fine. Okay, I'll stop here. We'll continue the lecture from the next class.